Welcome back. This is Mr. Hassan's Maths channel. I'm now going to be going through question number 2 from the International A-Level Edexcel Pure Mathematics P4 paper from June 2023. This question here is about, it looked like implicit differentiation. It says figure 1 shows a sketch of part of the curve C, which has equation 2 to the power of x minus 4xy plus y squared equals 13, where y is greater than or equal to 0. So it exists only above the x-axis. Okay, so that's, I guess, the range of this function. It says the point P lies on C, as you can see here, and has x coordinate 2. So this is 2 and yp. We don't know what the y coordinate is. That's 2 and yp. That's the coordinate there. It says find the y coordinate of p. So we've got to find the y coordinate of p. So basically, we know that at p you have 2, and we've got to find what yp is. So of course we take x equals 2, and we substitute into this formula, and then we can make y the subject of that formula, right? So we have 2 to the power of 2 squared, minus 4 times 2 times y, plus y squared equals 13. So we have 4 minus 8y plus y squared equals 13. So we see we have a quadratic equation. So if I rearrange this equation, let me just bring this up here. Okay, I'm going to make y squared minus 8y, and I'm going to subtract 13 from both sides. That's going to give me minus 9. Okay, minus 9. 4 minus 13 is going to be minus 9 equals 0. So I'll end up now something I can factorize. I'm pretty sure this factorizes. 9 and 1 will be my two numbers that multiply to give you 9. One has to be positive, one has to be negative. It must be negative 9 and plus 1. So we have y equals 9 and y equals negative 1. Now, obviously, y has to be greater than 0, so this is not one of the solutions. So therefore, we can say that y has to equal 9. So the y coordinate of p is 9. Okay, that's the y coordinate of p. So we reject the minus 1, of course, because the curve doesn't exist down there. Okay, so that's the answer to this question. Question number 1, part A. Okay, 1 part B, it says find dy dx in terms of x and y. Okay, so we got to find dy dx. This is where we have what's called implicit differentiation. And this is where I'm going to go into a bit of detail to explain, because a lot of people, they do some really strange things in a question like this. They will say, all right, dy dx equals, and then they'll start differentiating this like, you know, like dy dx equals, oh, that means differentiate this. Okay. Now, I want to go through some background a little bit about what differentiation actually is. And let's start with, say, y equals, say, 3x squared plus, say, 2x plus 1, something like this. Okay. When you are differentiating, an equation like this, you could say, what you're doing is you're differentiating both sides with respect to x. Okay, and when you differentiate a whole expression like this, it's like you're basically differentiating each part separately. So I know that, if I differentiate this side with respect to x, I'm going to get dy dx. That's what the differential of y is with respect to x. So what I've done here is I have differentiated this side with respect to x. And I'm also going to differentiate all of this side with respect to x. What I've done to one side of the equation, I've done exactly the same thing to the other side. All right, so I differentiate this side of the equation with respect to x, I have to do the same to this side. Now, what we end up with, if you differentiate y with respect to x, we're going to end up with dy dx. I'll go into more detail about that in a few minutes. But here, what we actually do is we don't write this down at all. Okay, all of this stuff we don't write down when we differentiate. Even in P1, we were doing this, but I'm just trying to give you the basis of it so that you'll understand why we do certain things when it comes to implicit differentiation. So what we're going to do, what we're actually doing is we know we can differentiate a whole expression by differentiating each term separately. So I'm differentiating 3x squared with respect to x, and I'm differentiating 2x with respect to x, and I'm differentiating 1 with respect to x. Okay, so when you differentiate 3x squared with respect to x, you get 6x. And when you differentiate 2x with respect to x, you get 2. When you differentiate 1 with respect to x, it's a constant, you get 0. So you end up with dy dx equals 6x plus 2. Now we just go straight from here to here. That's what we do from P1, P2, whatever. But this is stuff which should be understood in your mind. You don't have to write this down, of course, but you should understand that that's what's going on. What we're doing is, what we're doing to one side of the equation, we're doing the same thing to the other. We're differentiating each, the left side of the equation with respect to x, and we're differentiating the right side of the equation with respect to x. And you should understand that when you differentiate an expression made up of lots of terms, we can differentiate each term separately. Okay? If it's a product, no. For example, if it was 3x squared times sine x, no. As we'll see in a minute, we have to use the product rule. But if it's a sum of terms, we can differentiate each term individually and get our answer. So that's actually what's going on when you're differentiating something simple like this. Okay, so now what I'm going to do is I'm going to now hopefully, those of you who maybe had some doubts about implicit differentiation, now you might understand what's going on. In fact, I'm going to make some more space here. I'm just going to take this stuff to the other page so that we don't have issues with space. So I'll just cut this from here and paste it on this next page. Do that on this side. Give us some more space in case we need it. So now what I'm going to do is I'm going to differentiate every term of this whole equation with respect to x. So basically we're differentiating, and again, this line, you don't really have to write it down. I'm just, going through it. So we're differentiating the whole of this side with respect to x, which is 2 to the power of x minus 4xy plus y squared. And this side, we're also differentiating with respect to x. Okay, so basically what we end up doing is differentiating each term individually with respect to x. Okay, so now when you differentiate 2 to the power of x with respect to x, this is one of those of the form a to the power of x. If you differentiate that, it stays the same, but then you multiply by the ln of that constant a. So here it's going to be 2 to the power of x times ln 2. Then we have minus 4 times, and I've got x times y. So I'm going to take x times y, and as it's a product of two separate functions, I'm going to use the product rule. So I have x as u, and v is going to be my y. So I'm going to find u dash, which is 1, and now I'm going to find v dash. Now what is v dash? Well, it's the differential of y with respect to x. If I differentiate y with respect to x, I get dy dx. Simple as that. Okay, I get dy dx. Right? So you end up with y times v times u dash, so it's y, and I'm going to have plus x dy dx. So that's that done. So I've done this and this. Now y squared. How do I differentiate y with respect to x? Y squared with respect to x. Okay, so this is now the next step in. This is really what implicit differentiation, where people get a bit confused. And this is where I'm going to explain to you. Now, we know that y is some function of x. We can rearrange this to make y some function of x. So y has got x involved in it somehow, right? So just like you have, for example, if you differentiate, say, x plus 3 to the power of 5 with respect to x, you differentiate the main function. So you multiply by the power in this case, and you take 1 from the power. Okay, let me call this 2x here. You multiply by the power. So you multiply by the power, you take 1 from the power. So we'll end up with, let me just write it again. Supposing you have 2x plus 3 to the power 5. If you differentiate that, you're going to get 5 times 2x plus 3 to the power of 4. So you multiply by the power, take 1 from the power, but then, because of the chain rule, as we know, we multiply by the differential of what's inside the function, which is 2. So we end up with 10 times 2x plus 3 to the power of 4. Similarly with this, okay, y is like some function of x. So it's like something inside this bracket, you could say. So first thing is you multiply by the power, and you take 1 from the power. But then you have to multiply by the differential of what's inside the function. In this case, what's inside the function is y. It's like you got a y squared, just like we have here. So we multiply by the power, you leave this as it is, take 1 from the power, then you multiply by the differential of what's inside here. And what's the differential of y with respect to x? It's dy dx. So that's why you write dy dx at the end of it. Okay, so if you want to differentiate y squared with respect to x, you say, okay, multiply by the power, take 1 from the power, then we multiply by the differential of y with respect to x, which is dy dx. And that's equal to, if you differentiate a constant, you get 0. On that side, you get 0. So this is a little explanation here, hopefully, that will make you understand why we do that. We're dealing with, okay, things which are in terms of y. When we differentiate them with respect to x, we have to differentiate as normal and then multiply by dy dx, because that's what's the function inside the function, you could say. Right? So now we have differentiated each term on both sides of the equation with respect to x. We want to make dy dx the subject of this. Okay, so I'm going to expand this bracket to release this dy dx. So I have 2 to the power of x times ln 2 minus 4y minus 4x dy dx plus 2y dy dx equals 0. So what I'm going to do now is the terms with dy dx, I'll keep them on the same side of the equation. So I'll write this as 2y dy dx, okay, minus 4x dy dx equals, if I add this to both sides, I get 4y minus 2 to the power of x ln 2. I can take dy dx as a common factor of these two terms. So dy dx times 2y minus 4x equals 4y minus 2 to the power of x times ln 2. And then I can divide both sides by 2y minus 4x. So I say dy dx equals 4y minus 2 to the power of x ln 2 over 2y minus 4x. And there we have our gradient function, okay, the dy dx. Okay, now we could have at this stage, some of you might have done the opposite at this stage. They might have, for example, kept this on this side and said this is equal to 2y dy dx, or 4x dx dy dx minus 2y dy dx. So your answer could have in the end ended up as 2 to the power of x ln 2 minus 4y over 4x minus 2y. And this is also perfectly correct. Both of these are the same. They're the same thing. Okay? It's exactly the same thing. It's just like if you multiply the top and bottom of this by minus 1, you get that. So it just depends at this stage what you did here. Okay, in my case, I kept this, the dy dx on the left side, and the other things on the right side. You could have kept the dy dx on the right side by adding 4x dy dx and subtracting 2y dy dx. You would have ended up with the answer looking like that. But both of them are fine. And there's the answer to part B. So we have an expression for dy dx now, okay, which we might need. So I think I will copy that in case. Now, it says the tangent at C, or the tangent to C at the point P, crosses the x-axis at the point Q. Find the x-coordinate of Q, giving your answer in the form A times ln 2 plus B over C times ln 2 plus D, where A, B, and C and D are integers to be found. So let me just first put this over here somewhere. This is what we found dy dx to be. That's obviously going to help us with this question. So the tangent to C, the tangent to the curve at the point P would be a straight line. And that straight line would basically just touch the point P, okay, and have the same gradient of the curve at that point. So that tangent is going to pass through the x-axis at the point Q. This is the point Q, okay? We want to find the x-coordinate of Q, giving you an answer in this form. So to find the x-coordinate of Q, we've got to start or begin the process of finding the equation of the tangent. Okay, so we got to think about what is the equation of the tangent, and then when we have started the process of finding the equation of the tangent, we will realize we need to find where that tangent passes through the x-axis. So the equation of the tangent requires two things. One, it requires the gradient of the tangent, and two, it requires a point on the curve, which we know it goes through the point P, and P had the coordinates 2 and what was the y coordinate of P? 9. Okay, 2 and 9. So P has the coordinates 2 and 9. Okay, we found that in part A. All right, so what we need now is the gradient of the tangent at P. Okay, that's when x equals 2. So we're going to use our dy dx, which is the gradient function. This tells us the gradient of this function at the point, any point we want. So we want to find when x equals 2. In fact, we got in terms of x and y, so when x equals 2 and y equals 9. Okay, so we're going to use both of those because you have the equation is 4y minus 2 to the power of x ln 2 over 2y minus 4x. So now we're going to take the point 9. So we have dy dx equals 4 times 9 minus 2 to the power of 2 ln 2 over 2y, which is 2 times 9 minus 4 times 2. Okay, so dy dx is going to be, that's 4 nines, which is 36, minus 4 ln 2 over 18 minus 8, which is 10, right? 18 minus 8, which is 10. So if we simplify this, I think 2 can be taken out of this. You have 2 times 18 minus 2 ln 2 over 2 times 5. They cancel out. So we're left with 18 minus 2 ln 2 over 5. So that's the exact form of the gradient. So we say the gradient, okay, of the tangent at P is going to be 18 minus 2 ln 2 over 5. Okay, and we know that it passes to the point P is 2, 9. So we can start making the equation of this y minus y1 equals m times x minus x1. So if we start making the equation of the straight line, we have y minus the y coordinate of the point P, which is 9, equals m, which is all of this, 18 minus 2 ln 2 over 5 times x minus the x coordinate. Okay, we don't actually have to find the equation of the straight line because all we need here is to find the coordinates of Q where it passes the x-axis. Now, something passes the x-axis, okay, when y equals 0. So we're going to replace the y with 0, and then what we'll be left with, we have to solve for x. So we have 18 minus 2 ln 2 over 5 times x minus 2. And what I can do is I can multiply both sides by 5 and divide both sides by 18 minus 2 ln 2. So I have a minus 45 over 18 minus 2 ln 2 is equal to x minus 2. I can add 2 to both sides. So I have minus 45 over 18 minus 2 ln 2 plus 2 equals x. Now, we've got to write it in this form here. How are we going to do that? Okay, so what we're going to do is we're going to combine these into one fraction. So I have the same denominator, which is 18 minus 2 ln 2, and that's minus 45. And this will be 18 minus 2 ln 2, and this will be 2 times 18 minus 2 ln 2. I've just made them equivalent fractions. okay, with the same denominator. So now I can say x equals, I have one denominator, which is 18 minus 2 ln 2. And here I'm going to have minus 45 plus 2 times 18, which is 36, minus 2 ln 2. Okay, so we have to end up with something like this. So it looks like we're almost there. It looks like we've got the right tracks. So we're going to have here minus 45 plus 36. That's going to be minus 9, right? Minus 9. Okay, minus 2 ln 2 over, and here I have 18 minus 2 ln 2. And is that what we had to show? Okay, A, B, C, and D. So we have this is minus 4 ln 2. So if there's a mistake here, let me just correct it. Let's just go back. I forgot. So what did I do wrong? When I multiplied out this bracket, I said 2 times 18, and that should be 2 times minus 2, which is minus 4 ln 2. So I end up with minus 4 ln 2 minus 9 over minus 2 ln 2 plus 18. I can make it look neater by multiplying both the top and the bottom by minus 1, in which case I'll have x equals 4 ln 2 plus 9 over 2 ln 2 minus 18. That makes it look a bit neater. Okay, and there we have the answer to this question, part C. Right? It's a bit of palaver at the end here, just rewriting it, but we have to end up with ln 2's. Okay, A ln 2 plus B. So we have A, B, C, and D. Okay, 4, 9, 2, and minus 18. So that concludes this question, which is question number 2 from the June 2023 paper. I think that was it. Yep. Okay, so other questions from this particular paper can be found in the playlist. That will be appearing at the top of the screen here, top right of the screen. Other questions from the topic of implicit differentiation in the playlist over here. You can subscribe to my channel by clicking on this link. And at the top here, you can find a video, link to a video, which will tell you how to use my channel to find what you're looking for. Thank you for watching, and see you soon.